second derivative is equal to 0 or the second derivative does not exist, and both of them are inflection point. For the second derivative is equal to 0, we have this one, which is the previous example, y is equal x cubed plus 9 over 2x squared. Here we have the second derivative is equal to 0 at the point minus 3 over 2. For the second graph here, we have the second derivative does not exist at 0, but the function has an inflection point at 0. Now, how can we use the second derivative to know if the function has relative maximum or relative minimum? So, Theorem 473, second derivative test, let f be a function for which f double prime exists on an interval a to b that contains the critical number c. If f double prime c greater than 0, then fc is a relative minimum. If f double prime c less than 0, then fc is a relative maximum. If f double prime c is equal to 0, the test fails, and fc may or may not be a relative extremum. In this case, use the first derivative test. So first you need to find the first derivative, then you need to find the critical number, then you find the second derivative. Then you check the second derivative at the critical number. If the second derivative at the critical number greater than 0, then the function has relative minimum. If the second derivative at the critical number less than 0, then the function has relative maximum. But in case you find that the second derivative at the critical number it is equal to 0, so you say that the second derivative test is fail, and you have to return to the first derivative test. يعني إذا نحن بنستخدم السكند derivative test، أول خطوة بجيب اللي هي الf برايم x، بعدين بطلع الكريتيكال نمبرز، بعدين بجيب المشتقة الثانية، بشيل الكريتيكال نمبرز وبعوضهم في المشتقة الثانية. إذا الناتج للسكند derivative عند الكريتيكال نمبر يطلع greater than 0، إذا على طول بقول الفانكشن عندها relative minimum. إذا السكند derivative عند الكريتيكال نمبر أصغر من الزيرو، إذا بقول إن الفانكشن عندها relative maximum. لكن in case إنه كان عندي السكند derivative عند الكريتيكال نمبر يطلع الناتج يساوي 0، إذا هنا بقول إنه السكند derivative test fail وما أقدر أستخدمه، برجع لي الفيرست derivative test اللي هو بجيب الكريتيكال نمبر، بشوف القيمة اللي الفيرست derivative قبل الكريتيكال نمبر وبعد، لو كانت increasing بعدين decreasing إذا بقول إنها relative maximum، ولو كانت decreasing بعدين increasing بقول relative minimum. طبعا أي واحد نستخدم على حسب السؤال. إذا السؤال قال استخدم second derivative, so you have to use the second derivative. But if it is an open question, so you may use the first derivative, you may use the second derivative. It is up to you. So now let us see this example, which is question number 22. Use the second derivative to locate all points of inflection if fx is equal to cosine x. So here we have to use the second derivative. So we need to find f prime x, we need to find the critical numbers, then we need to check the second derivative at the critical numbers. So if fx is equal to cosine x, that means f prime x is equal, derivative of cosine will be minus sine. Then the derivative of the second derivative f double prime x is equal minus cosine x. So now f double prime x is equal to 0, that means f minus cosine x is equal to 0. So now to solve minus cosine x is equal to 0, we need to find all the values that give us minus cosine x is equal to 0. So x is equal by over 2, 3 by over 2, 5 by over 2, etc. So x will be by over 2 plus k pi, where k is an integer. So for the second derivative f double prime x, we need to check it before and after this interval. So, or before or after these values to know which of them are point of inflection. So here we have minus by over 2, then by over 2, 3 by over 2, 5 by over 2. We get this value when this one does not exist, when this one is equal to 0. We choose some of them, not all of them. So I'll take minus by over 2, by over 2, 3 by over 2, 5 by over 2. So then f double prime x less than 0 for x in the interval, we see from minus by over 2 to by over 2, then from 3 by over 2 to 5 by over 2. So we conclude that f is concave down. For f double prime x greater than 0, we see here x for x in the interval from pi over 2 to 3 pi over 2, then from 5 pi over 2 to here 7 pi over 2. So we conclude here f is concave up. So since function change concavity and it is the second derivative is equal to 0 at these all points, we conclude that f has inflection point at pi over 2 plus k pi, where k is an integer which is nz. So first you find the first derivative, then you find the second derivative. To find the inflection point using the second derivative, then you need to find the second derivative when it is equal to 0. So solving this will give us some point, but you cannot conclude these are points of inflection unless you check the concavity before and after this point. So you will take for these numbers, then you will check the second derivative. If it is less than 0, that means your function concave down. If it is greater than 0, that means your function is concave up, and so on. Then we have example 3. Let fx is equal x cubed plus 1. Find relative extrema if f has any. So to find the relative extrema using the first derivative test or the second derivative test, it's up to you. So first we need to find f prime x, which is equal for x cubed. So now f prime x is equal to 0, that means for x cubed is equal to 0. So x is equal to 0 is the critical value, since it is in the domain of our function f, and the derivative is equal to 0 at 0. So if we want to use the second derivative test, we need to find the second derivative. Then we need to check the second derivative when x is equal to 0. So f double prime x is equal, the derivative of 4x cubed will be 12x squared. So now we need to check the second derivative at the critical value. So f double prime at 0, this will give us 0. And here we cannot conclude. So we conclude that the second derivative test fails, and we need to back to the first derivative test. For the first derivative test, we need to take the interval from minus infinity to 0, then from 0 to infinity. We need to check the value of f prime x. So here from minus infinity to 0, f prime x is negative, that means our function decreasing. For the interval from 0 to infinity, f prime x positive, that means fx is increasing. So your function decreasing, then increasing, that means your function has a relative minimum at the point 0. So f0 will give us 1. So f0 here, this one should be 1, not 0, sorry. So f has a relative minimum at f0, which is equal 1. Because if you replace x here by 0, you will get it is equal 1. Now we have another example, which is question number 31. Fx is equal 6x power 5 minus 10x cubed. Use the second derivative test when applicable to find the relative extrema of the given function, then graph and find the intercepts and point of inflection when possible. So for this first, we have f of x is equal 6x power 5 minus 10x cubed. So if we take 2x cubed as a common factor, here we have 3x squared minus 5. Now to find the x-intercept, because it says find the intercept. So if you find the x-intercept, you need to put y is equal to 0. So this function should be all equal to 0. That means either 2x cubed is equal to 0, which gives us x is equal to 0, or 3x squared minus 5 is equal to 0. That will give us x is equal plus or minus root 5 over root 3. So we have 3x-intercept, 0, 0. Root 5 over root 3, 0, minus root 5 over root 3, 0. For the y-intercept, you need to put x is equal to 0. So if x is equal to 0, that means y is equal to 0. So here we have the point 0, 0. Now to find the critical numbers or the relative extrema using the first derivative or the second derivative, we need to find f prime x. So the derivative of this one, 6 multiplied by 5, 30, x power 4 minus 3 multiplied by 10 will give us 30x squared. So if we take 30x squared common factor, we left with x squared minus 1. So to find the critical numbers, f prime x is equal to 0. That means 30x squared multiplied by x squared minus 1 is equal to 0. So either 30x squared is equal to 0, which give us x equal to 0, or x squared minus 1 is equal to 0, which give us x is equal plus or minus 1. So now we have three critical values: x is equal 0, x is equal 1, x is equal minus 1. Since all of them are in the domain of our function f of x, because it is a polynomial, and the derivative is equal to 0 at these 3 points, so we conclude they are critical values. Now, to use this, use the second derivative test. So first we need to find the second derivative. So f double prime x, we need to differentiate this one again. So this is the first derivative. The second derivative will be 30 multiplied by 4, 120x cubed, minus 2 multiplied by 30 will give us 60x. So now we have the second derivative will be 60x multiplied by 2x squared minus 1. Using the second derivative test, we need to check this second derivative at 0 and at plus 1 and at minus 1. So f double prime 1, this will give us 60 multiplied by 2 minus 1, this will give us 60, which is greater than 0. So f has a relative minimum at the point which is give us f1 is equal 6 multiplied by, so here we'll replace x by 1, 6 minus 10 will give us minus 4. So we have a relative minimum at the point 1 minus 4. And f double prime at minus 1, so replace x here by minus 1, we will get minus 6. So minus 6 less than 0, we conclude f has a relative maximum, f minus 1, which is give us, so replace x here by minus 1, we get minus 10 multiplied by minus 1, so minus 6 plus 10 will give us 4. So here we have relative maximum. Then we need to check when x is equal to 0, so f double prime x at 0, this will give us 0. Because if you replace x here by 0, you will get 0. So the second derivative test fails, and we need to use the first derivative test to know what is the type here of the relative extrema. So to use the first derivative test, since we have three critical numbers, 0, 1, minus 1, so we need to check at 0. So here we have minus 1, 0, then 0, 2, 1. We need to check the sign of f prime x. So from minus 1 to 0, we need to take any number, substitute in the first derivative. This will give us negative. Then from 0 to 1, take any number, substitute in the first derivative here, we will get also negative. So your function decreasing, then decreasing, so we conclude there is no relative extrema at x is equal 0. So just we have two relative minimum when x is equal 1, relative maximum when x is equal minus 1. To know the point of inflection, you need to find the second derivative, then you need to check if the function change concavity. So we have here the second derivative, 60x multiplied by 2x squared minus 1. So 60x multiplied by 2x squared minus 1 is equal to 0. Either 60x is equal to 0, this will give us x is equal to 0, or 2x squared minus 1 is equal to 0, that will give us x is equal plus or minus 1 over root 2. Once you find the second derivative is equal to 0 or does not exist, you cannot conclude that the function has inflection point at this point. First, you need to check if the function change concavity at this point. So here we will take the critical value with this value to check the concavity of the function. So we'll take from minus 1 to minus 1 over root 2, then from minus 1 over root 2 to 0, then from 0 to 1 over root 2, then from 1 over root 2 to 1, to know if these are point of inflection or not. So from minus 1 to minus 1 over root 2, we have the function, the second derivative negative, so that means it is concave down. For the interval from minus 1 over root 2, we get it is positive, so that means our function concave up. For the interval from 0 to 1 over root 2, the function is negative, so that means the second derivative is negative, that means our function concave down. For the interval from 1 over root 2 to 1, the second derivative is positive, so that means our function concave up. So here we see that all the function change concavity all these 3 points. So we conclude this 0, 0, minus 1 over root 2, 7 over root 8, and 1 over root 2 minus 7 over root 8. All of these 3 are point of inflection since the second derivative is equal to 0 and its change concavity at this point.